inquiry. Without the title up there to cheat, it's a little hard.
So, thank you all for coming. I really appreciate seeing faces here on Saturday afternoon. A couple of years ago, my department and the whole campus added a senior inquiry capstone experience, and we realized we ought to prepare our students to ask and explore their own questions, or this is going to be a horrible failure. And so I see that sort of student inquiry as the intersection of sort of my IBL courses and so my understanding of individual inquiry, whether it's sort of the psychology of an individual student asking a question or research, professional research. So, okay, and the arrows represent both sort of the flow through time and the influence of ideas, crossing back between those domains, ending with some of my thoughts about my courses. Along the way, I hope to offer three sort of basic suggestions about tasks that might support this kind of learning, as well as perhaps a provocative question about what it is we're actually doing in our courses. So this whole thing starts with my IBL experience, which sounds great, but I actually think it's a little bit ironic. In the sort of the traditional IBL experience in both my own experience as a graduate student and in many of my courses, we provide the definitions and the theorem. So the students they're doing something meaty. They're proving, why are these results true? But in many ways, they're not asking very many of their own questions. There is a little bit of room for that here and there, but in some ways I feel like they're not asking a lot of the questions. So although I do see a connection to teaching this student inquiry, there's a disconnect. I have to do something different. And so I moved from my IBL experience to an understanding of inquiry. I don't know about the rest of you, but no one ever taught me how to do research. No one has ever said, oh, these are the kinds of things you do. And all the understanding I have of that process comes from my IBL teaching and reflecting on that process. And over the years, I've developed a heuristic, a scheme for thinking about the basic steps. So I thought I'd share that scheme with you. And I'm going to use graph theory examples, both because the students in the class that I'll talk a little about did a lot of graph theory, and also because many people know enough that you'll already know the definitions. So you might start with a question like the Königsberg Bridge problem. Can you cross the 7 bridges of Königsberg, coming back to where you started without reusing a bridge? Eventually you abstract from that to the definition of a graph and the definition of an Euler circuit. You explore definitions. You want to know, so what are these properties of a graph? What is this thing that I've just defined? You explore, you investigate your definitions, and you make conjectures. For example, here are all of the graphs with 5 vertices and no vertex at degree 0. And you start categorizing them. How many of them seem traceable? How many of them seem like they have an Euler circuit? And you begin to conjecture, oh, maybe in these kinds of situations I'm going to be able to find an Euler circuit. Which you say as a conjecture, and eventually through justification and proof turn into a theorem. And sort of the last step is you return to your question by applying. You say, in this situation and only this situation, I have an Euler circuit. My original object, the city of Königsberg, does not meet those conditions, so therefore there is no Euler circuit. And then you realize along the way all kinds of other things, circuits and paths and planarity and degree and all these other things came up, and so extension allows you to ask new questions. So this is a version of what I think the process of exploring a mathematical idea is. And so as I was preparing to teach this course, I was also finishing up a textbook, Mike Starberg, an inquiry-based textbook. And this scheme played a strong role. We had already done some work with sort of, the thing I'm most proud about in this book is that rather than just asking them, giving definitions and asking theorems, there's meta-content spread throughout about the process of inquiry. And then at the end of each of the units, there's a sort of a distillation, that's where the title comes from. Distilling ideas. A distillation of the process of inquiry. I have copies of the last page of the graph theory chapter, if you'd like to see what that distillation looks like. But it's missing the embedded comments about, oh, we ask these kinds of questions in these kinds of situations along the way. Graph theory, for me, represents the sort of biggest view of the process of inquiry. We sort of go through the whole cycle. We do that with groups and epsilon delta calculus, but in groups, we focus more on when you explore the exploration, when you explore a definition, it sort of feels categorical. When you study objects, sub-objects, products of objects, maps between objects, those things that we do every time we see a new definition as mathematicians, the goal is for them to understand that that's one of the big habits. And then epsilon delta calculus, the hard part there is abstraction. When you go from approaching to what is this definition. So each of those two chapters delves more deeply in. And this really came from years of work, but having to think, I have to teach students how to do this. I don't have to, they can't just do it. I have to help them see it. So I have this book now, and now we're moving towards me actually teaching this class in which I try to teach my students to ask and explore their own questions. And it seems clear that reflection on inquiry is a really key component to that. So here's the first of the three sort of course assignments, tasks that I think could help. I actually have this class, which comes after a discrete math class. I have them read the graph theory chapter of the book. Take notes on the inquiry moves, not the content, the kinds of questions that are being asked. And then as a class, we produce a visual representation of the flow, the kinds of things you do when asking and exploring a mathematical question. So that scheme before, they basically reinvent it. It's not surprising that it always looks kind of like that because of the thing that they're reading. But I guess what I'm suggesting is, if you can get them to read something where they won't be too bogged down in the content, either the content is really easy or they're familiar with that content, you can ask them what are the kinds of questions that were asked, not just what facts occurred, but you can ask them to reflect on the process and then reinvent it. And so, as you can imagine, the first class for them where somebody says, okay, I'm not going to tell you anything, I don't care what the content is here, just ask your own question, good luck, is terrifying and overwhelming. But because of this activity, I could say, what I want you to do is that. I'll break it down into some steps for you, but that's what I want you to do. So this is really how I communicated what the big project in the class was going to be. You're going to do that. So assignment number 1. But there was a second level, which is that just doing that was probably not enough for them to internalize the habits of inquiry. So they needed to reflect on their own actions as they were doing it. And I was inspired by some things that my friend Elizabeth Thorin regularly does for her own research, but also something she's done with her own inquiry students at Santa Barbara, which is, I'm calling here research journals. So every time they had an assignment, it came with these sort of standing questions, and sometimes they're described in a little more detail. But it was sort of a reflective blog post, so they all had e-portfolios that the department had started doing. And there were 3 components to what they had to do after they'd done all of their scratch work, and they actually had those little black and white notebooks where they were supposed to work in them. But these were reflective components that they put online. There were 3 parts, and they were activity. What did I do? I drew all the connected graphs that I could think of with 7 vertices, and I tried to figure out how many Hamilton cycles I could find in them. Questions, what would I do next? Well, it really seems like the symmetric ones, the number of Hamilton cycles I can find is a lot smaller, a lot higher. I should look at which one, how these numbers relate to symmetry. That would be a good thing for me to investigate. I have the raw data, but I haven't asked that question yet. And what do I now know? Things like, you could just list, this graph has this many Hamilton cycles, or it could be something bigger. It could be a more sort of conjecture-like level. So this is assignment number 2. So reading something where they can reflect on the process of inquiry and actually reflecting on their own inquiry as they're doing their work all the way along. So what did the course end up looking like? So I actually moved to this student inquiry. The third classroom activity is the phases of the big project in which the students asked and explored their own mathematical question. So there are 6 phases here. It really felt more like 4. And these projects took my students about 3 or 4 weeks. So the first one is to describe a mathematical phenomenon. I use the phenomenon to mean something that's not yet technical. So an example here from students who presented on Thursday morning at this conference was I made a paper airplane and then I unfolded it and the paper has these creases and it looks kind of like a graph. this might be an interesting thing to study. Get your hands dirty with examples. I made 100 paper airplanes. Here are the kinds of things. So they blend together. They start noticing things about them. Oh, and along the way, I want to pin down exactly what I mean by paper airplane. Can I fold something, unfold, fold in a different direction? Is that allowed or not? Sort of making their definitions precise. Organizing their examples and articulating patterns. All the intersections in the middle of the paper appear to have even degree. So that's kind of interesting. What's going on there? Does everything have that? And then they state conjectures and test with examples. Well, they don't. Not every vertex has even degree, but I can articulate a process of adding a couple of folds to a given diagram where I can turn it into something where every vertex has even degree. They were really excited about polar circuits, and I saw the even degree. And refine the conjectures and justify them into theorems that really show that that process works in all situations. Hey, and colorability is an interesting thing. Are these graphs colorable? They all look 3 colorable. That's really cool, because didn't we learn something about planar graphs being 4 colorable? Maybe things that are made in this procedure are always 3 colorable. But we produced an example, and then we tried to turn it from a regular graph into one that has an Euler circuit, and that process turned our very worst 3 colorable graph into one that's actually 4 colorable. So it doesn't appear that this actually forces 3 colorability. But we found something cool, and that seemed like almost a really neat theorem. And then the final step, because I was at the joint meetings, was they took a week to reflect on this inquiry process and make a video. And it's about a 6.5 minute video. It's on YouTube. I think it's called Folds and Fixes. If you like, I can email me or just look me up and our list on YouTube. And they shared the process and their results. And they use that video in their talk on Thursday morning. So these steps: describing the phenomenon, examples, articulating patterns, testing them, conjecturing and trying to justify, and then eventually sharing them. So this highly adaptable. And at each phase, they were writing a research journal reflection post about things that they thought they might do. So what am I really trying to do with this talk? I would say the conclusion is that students can ask and explore their own questions, but it may take some more support from us. And part of that support might be getting out of the way, asking fewer of those questions ourselves, and really thinking about where is the space where they might ask some of their own questions. For those of you who are part of the lingo, let's say, I'd like to offer some vocabulary for. You can have the slides later if you want. So I think of at least 4 kinds of discovery-based mathematics. So inquiry-based, the way I've been talking about it here, we often give them mathematical objects, which is different than the phenomenon. That's the precisely defined ones, and many of the theorems, probably not all, but many of the theorems. And they prove those theorems. So they ask, why is this true? Exploration-based, in which maybe we give them the objects, and they play with them to say, well, what appears to be going on here? What should be true? So they're stating the theorems, and they may or may not get to proving those theorems. Guided reinvention. Tim Baster did a lovely job of connecting our community with theirs on Friday in his talk. But there we give them maybe a mathematical phenomenon, not a precisely defined object. And the big work they do at first is to figure out what the definition of that object should be, and then they may go a lot further. And then student research, where the whole agenda is open. And so I sort of see this as a sliding scale. And I'm kind of suggesting that they should be mixed. So what would this look like in a class? Future course. I'm teaching abstract algebra this fall, and I'm really excited about it. The reason I'm a mathematician is I remember proving that a group has a unique identity. I know that's like a ridiculously lame theorem, but that's the reason I'm a mathematician. It is. So I see these 4 things appearing in this course. What I'm hoping to do is an exploration of structure to define groups. So giving them, I'm going to use the group chapter of the book. And we start with addition of numbers, multiplication of integers, multiplication of reals, and transformations of a triangle. And they're already pretty well defined mathematical objects, but we distill from that the definition of a group. So they're engaging in that definition making, but it's pretty structured already. And then we're going to do an IBL development of group theory. Then we're going to step back, and we're going to do a guided reinvention of rings. I'm going to do a project with Milos and John Paul Cook, who's done a little research in data reinvention of rings, to prompt them to make the definition. And then my learning objective for the course is that they understand those categorical questions we ask about an object. Objects, sub-objects, products between them, maps between them, things like that. And because we've just done group theory, I'm going to say, okay, you've got your definition of a ring, you know what you want it to be. What are the theorems you ought to be stating? What should you be doing? And so it's going to be a research, I hope, research-like experience where they say, well, maybe this is true, and is it like this other theorem that we've got written up somewhere else, and can we take that and make that a theorem in ring theory as opposed to in group theory? So, the goal is that they actually understand the process of asking about a mathematical object, not just that they happen to do that process twice because of the way we talk about groups in the rings. Again, we talked a little about how I blended my IBL experience and my understanding of individual inquiry to get at this student inquiry where they understand the process. And then hopefully I've been a little provocative about making room for them to ask a little bit more of their own questions. Thank you.